Now, yes. Yes, that is a 2. Let me make it clearer. All right. Now, let's multiply both sides by cos of omega nt, and then integrate from minus t by 2 to t by 2. What does that give us? It gives us a0 by 2. This term is not dependent on time, so we can bring it out of the integral. Minus t by 2 to t by 2 cosine of omega nt dt plus summation m equal to 1 to infinity am integral minus t by 2 to t by 2 cosine of omega mt cosine of omega nt times dt plus summation m equals to 1 to infinity bm mt into cosine of omega nt dt. So now you can see these integrals here are the same form as the integrals we had before. We discussed about it here. This one and this one. Okay? So we now know that the second integral is 0 no matter what. Now the first integral is 0 for all the terms except one m is equal to n. So from m being 1 to infinity, there is only one term which is non-zero, and all the rest of the terms go to 0. So that gives us integral minus t by 2 to t by 2 x of t into cos of omega nt dt is equal to, so what do we get? This coefficient will be an, but when m is equal to n, this is nothing but an times this integral which we have, cosine of omega mt, cosine of omega nt. When m equal to m, that value is t by 2. So essentially we are left with t by 2. So that means an is 2 over t integral minus t by 2 to t by 2 x of t into cos of omega nt dt. So in this expression, we began by multiplying our x of t signal with cosine of omega nt. Instead, if we multiply it by sine of omega nt, we will end up with an exact similar relation for bn, which is given by 2 over t integral minus t by 2 to t by 2 x of t into sine of omega nt. So, given any signal x of t, we can actually find out its Fourier coefficients using these equations. And once we have the Fourier coefficients, our life is made easy because all all it is a series of sums of harmonic components, and we already know how to analyze harmonic components. Does everybody follow me so far? Yes, no? Any questions? Come on, guys, you got to be more responsive. I can't see you guys very clearly. Does everybody understand? Yes? Okay. Okay. All right, sure. So I can go a little slower. That's fine. You need still some more time to copy down? All right. All right, I'll put the derivation back up. You can go over it again. I'll give you a minute. Any questions so far? You want me to go over anything again? Can you repeat the question a little louder? I cannot seem to get that. Oh, okay. Yeah, we will go over it. So give me a minute. So we're going to shift gears in a little while and go back to MATLAB. And I'll kind of exactly show you how this thing helps us get things. Just give me a minute, okay? It will be clear in a little while. So what essentially we are trying to do is put together an expression for any periodic signal in terms of its periodic coefficients. So once we have these coefficients, we don't have to deal with the original signal anymore, but rather we deal with a sum of series of harmonic components with amplitudes an and bn. And since we know these components have harmonic behavior, it's easy for us to get the expression for velocity and acceleration. And we will see that in the future, when we want to solve equations of motion, this thing actually comes in very handy. But I do understand your question as to why are we doing this, and I will show you how exactly these things relate back to the harmonic components. I'll show that using MATLAB in a little while. Okay, so let's proceed a little ahead so that we can finish this up and go into the MATLAB thing. Okay, where was I? Okay. So now we look at what is known as complex Fourier series. So From the complex number theory, which we discussed in the last class using the Euler's equation, we know that e to the power I omega t is nothing but cosine of omega t plus I sine of omega t. And similarly, e to the power minus I omega t is cosine of omega t plus I, sorry, that's my mistake, minus I sine of omega t. So if we add these two together, we get e to the power I omega t plus e to the power minus I omega t is equal to 2 times cosine of omega t. Or in other words, cosine of omega t can also be expressed in the exponential form plus e to the power minus I omega t by 2. Similarly, we can also see if instead of adding the two together, if we subtracted one from the other, we would result in an equation which gives us an expression for cosine of sine of omega t given as e to the power I omega t minus e to the power I omega t by 2 times I. This thing can also be written as minus I by 2 e to the power minus I omega t minus e to the power minus I omega t. That's because we already know I is nothing but square root of minus 1. So I square is minus 1. I to the power 4 is 1. And when we have 1 over I, and we write 1 as I to the power 4 by I, you get I cubed, which is I squared times I, that's minus I. So that's how we got the above expression for sine of omega t, the second one. Okay, so now what we do is put these expressions for cosine of omega t and sine of omega t and bring them back and plug it into your original Fourier series, which was given here into this equation. So we replace cosine of omega t and sine of omega t with those complex number forms. And what we resultantly get, so let's see what do we get. So we had x of t as a0 by 2 plus summation m equals 1 to infinity am cos of omega mt plus bm sine of omega mt. So wherever you don't understand, please stop me there, because since I cannot see you nodding or really figure out if you have understood or not, you have to be vocal about it, and that's the only way I'll know whether to go slow or am I going fast and so on. Okay? Alright, cool. Okay, so now let's put our complex form. So we had cosine of omega mt is given by e to the power I omega mt plus e to the power minus I omega mt over 2. And we had sine of omega mt given by e to the power I omega mt minus e to the power minus I omega mt divided by 2 times I. So now our x of t, upon substitution of these two into the Fourier series, gives us a0 by t, no change in that, summation m equals 1 to infinity am e to the power I omega m t minus I omega m t over 2 plus bm, and we'll use the alternate form, which is minus I over 2 e to the power I omega m t minus I omega m t. So e to the power I minus I over 2 times e to the power I omega m t okay. And now we will collect coefficients of e to the power I omega m t. So we have two terms here. So we can rewrite this sum as a0 by 2 summation m equals 1 to infinity am minus I bm by 2 into e to the power I omega m t plus am plus I bm by 2 minus I omega m t. We can further write this as summation m equals to, so you can see that if I substitute m as minus m, we're basically getting a conjugate of the complex number. So if we define, what you call, okay, let me just write this down, minus infinity to infinity Cm e to the power I omega m t, and that where Cm is equal to An minus I bm by 2. And when m is equal to 0, so C0 is equal to just A0 by 2, because there is no B0, right? So that's the complex form of the Fourier series. I'll give you a minute to copy. So the advantage of using complex Fourier series instead of the real Fourier series with AMs and BMs is the idea that in this case we only have to deal with one complex number per frequency and not two constants, and the information is together in a complex number, so in the form of real and imaginary parts. And it also allows us to use the exponential form, and which is more convenient than the cosine and the sine form. And that we will realize when we go into random vibrations, and hopefully will be a little much later than today. Okay, so now that we know that we can express it as a complex Fourier series like this, can we also get expressions for Cm like we got expressions for Am and Bm? And the answer is yes, we can. And it's quite straightforward because we already have the expressions for Am and Bm. Cm is equal to half of Am minus I Bm. Now, we know that expressions for Am and Bm, we just derived them, so we just substitute those. Minus I times so in other words, we can combine them into one form. Sine of omega mt minus I sine omega mt dt. And we know from Euler's formula that this is nothing but e to the power minus I omega mt. So we put that in, and we have got our expression for complex Fourier series. Some of these integrals can be, computational effort on some of these integrals can be minimized if we are able to express our original function x of t in terms of an even or an odd function, and it's always possible to express any signal x of t as a sum of even function t plus an odd function of t. So even function e of t has the property that e of minus t is equal to e of t, and odd function O of t, O of minus t is minus O of t. So this is how the even and odd functions are defined. So this is the definition of an even and odd function. And using that expression, we can see that if we are integrating from minus t by 2 to t by 2 of an even function times sine of omega mt, then the resulting integrand is an odd function because sine itself is an odd function, which you can see sine function looks like this. So if I go some value t here and minus t here, you can see that the value here and here, so let's say the value here is sine of t and the value here is sine of minus t, which is nothing but minus sine t. So it actually follows the definition of odd function. So sine of t is equal to minus of sine t. So since they are opposite, sine is an odd function, and you multiply that with an even function, you have an odd integrand, and that integral is 0 because it's symmetric about the y-axis, or more so anti-symmetric about the y-axis. Similarly, you can show that minus t by 2 to t by 2, odd function times cosine of omega mt is also 0, and that's because cosine of omega nt here is an even function. Cosine of t looks like this. So any point t you take, this is cosine of t, and this is minus t, cosine of minus t is equal to cosine of t. So therefore it follows the definition of even function. So whenever you have an odd integrand being multiplied across the x-axis, is anti-symmetric about the x-axis, or is essentially an odd function, the integrand, the integral will be 0 for that integral. And these two integrals can actually help you minimize some of the computational effort required in finding out the Fourier coefficients. Okay. One final thing, and then we go over to MATLAB, and you probably can practically see and appreciate why Fourier series is important rather than in a mathematical term. So the final thing which I want to go over is called a Fourier spectrum. And Fourier spectrum is nothing but a plot. So it's a plot of square root of an square plus bn square versus n, and also a plot of tan inverse bn over an versus n. So basically what we are saying is we want to calculate the phase. So this quantity here is called the phase, and the top quantity is called the amplitude. So this is amplitude versus n, and this is phase versus n. Okay. Now let's take a look at an example, and then we'll try to implement the same example in MATLAB to try to give you guys a little bit of an idea. So in particular, if I'm looking at this figure 1.2.2, and it is the Fourier spectrum for the pulses shown in problem 1.1.6. So let's go and take a look at 1.1.6. All right. Does everybody see this picture clearly? All right. Okay. So we are now given a signal which looks like this, and we want to calculate what its Fourier series is, or what its Fourier coefficients are, so that we can use to calculate its velocity and acceleration. Okay? In this case, we can actually do that without having the need to construct a Fourier series, but in more complex signals that will be very required. So this example is kind of a precursor to show you how the Fourier series application is brought into picture. Now, what is the period of the signal? Two pi, right, correct. So it repeats every 2 pi intervals of time. Now, the signal lasts for actually k times pi, and then there is a blank. There is like no signal for the rest of the time until it reaches 2 pi again. And that k times pi is given by the value of k, which in this problem they want to solve you for k equal to 2 by 3. But in the example shown in the other figure, they are actually using the value k equal to 1 by 3. I don't know if that's clear enough. Let's try to zoom. Alright, so they want you to do it for k equal to 1 by 3. So let's try to run this example in MATLAB and see, just to get you a feel of how things can be done and what Fourier series actually allows us to bring. Okay, Chandran, I lost the video, so it seems I can't see the class right now. Is there any way we can fix that? Okay. Okay, good. Now I can see them again. Great. Okay, let's try to increase the font here. How do I increase the font? Command window, fonts. Alright, so this one, let's make it 18. Apply. Okay, can everybody see this clearly? Okay, cool. So this is basically MATLAB. I'm guessing all of you are familiar because most of you have taken the course on what you call applied numerical methods, right? One second. Okay, so coming back. So the first few lines here is just to set my plot type. So what I have done is change the axis font name to Times New Roman and set my font size to 14 so that my labels are bigger so that you guys can see. And finally, I'm trying to increase my line width so that the plots are thicker. Now, we go back to the problem. So we have our signal which we want to simulate first. So let's first create the signal before we can find its Fourier coefficients. So we take k equal to 1 by 3 as was suggested in the book. Now, our period is 2 pi. So our fundamental period is 2 times pi as we saw from the signal. And Nmax, I'll come to it. So Nmax, what I mean is I'm trying to calculate the first 15 Fourier coefficients. So this is the value of n. As we go increase, we can have more and more number of coefficients. So the time, I create the time array from -2 times t to 2 times t, and I put 1000 points between them. And similarly create the X array. So does everybody follow this piece of code here? So as long as within one cycle of 2 pi, the value of time is less than k times pi, the value is 1. When it is more than k pi, its value is 0. And this thing will repeat every 2 pi. So let's run it so far up to here. Here, run section. So what we get here is your signal. Okay, where do I put this? Okay. So now you can see that this is how our signal looks like after we simulate it. So x of t versus t, and we have currently plotted it for 2 times of t, minus 2 times of t to 2 times of t, right? So you can see we took our time from minus 2 times of t to 2 times of t, and since t itself is 2 pi, we are essentially simulating from minus 4 pi to 4 pi. And since pi is roughly around 3.14, 4 times that is somewhere close to 12. So that's what you see on the x-axis, minus 12 to 12. And this is how your signal looks. Good. So now we have the signal done. What next? Now let's calculate the Fourier coefficients for the same signal. So here I define arrays, A1, B1, and C1. They have the same meaning as we saw in our lecture. So A is the harmonic components associated with the cosine terms, and B is the harmonic coefficients associated with the sine terms, and C is the complex form. So let's see what we are doing. So we run from n equal to 1 to n max. So n max is the number of Fourier coefficients, maximum number of Fourier coefficients I'm going to evaluate, which we have set here as 15. So we are getting the first 15 Fourier coefficients. Okay, so again, if we go back to your notes and look, we saw that our expression for our expression for an and bn is okay. Let me try to put this together. Okay. So our an is given by 2 by t minus t by 2 to t by 2 x of t cosine of omega n t dt. So that's exactly what we're doing. So trapezoidal function here means that we're going to do a trapezoidal integration with respect to t over x into cosine of omega n t. And omega n is nothing but n times 2 pi over t, as we saw in the lecture. So that's what we have put here. Similarly, bn is done the same way, except instead of cosine, we now have sine. And the complex form is nothing but half of an minus I times bn. Does everybody follow so far? All right, good. So now what we do is simply get the Fourier series amplitudes, which is given as your square root of an square plus bn square, which is nothing but the absolute value of 2 times c1. So I have just used a simpler notation here, but it is exactly the same. And the phase is calculated as a tan, or tan inverse, of b over a, and we convert it into degrees using this multiplication factor. The rest of the thing let's not worry about so much. I'll come back to it a little later. And let's run this code. Okay. So this was our original time series. Let's put it here. And this is our calculated Fourier coefficients. And if you go back to the book and see, that's exactly the plot which we have got on that page. Okay, so now let's come back to the original question. So why we need the Fourier series? So let's try to plot these Fourier coefficients together. Alright, so I don't think I have the code for that, but then we can do it right away right now. It shouldn't be a problem. So if we type C1, we have one of the 15 coefficients here. So now we know A1, 1 corresponds to the constant term, so by 2. Alright, so let's see X reconstructed plus A1, 1, 2 times cosine of 2 into pi over t times t. So let's plot the original signal, comma t, comma x reconstructed. So this is your original signal, which you see in the blue, and now we have included one Fourier term. So this is how we are approximating the first Fourier term. It looks pretty bad, doesn't it? Yes. But now let's keep adding more terms to it. Oh, sorry, I completely forgot to add the B1 term as well. Sorry about that. Sine of 2 into pi over t. So you can see that the peak value does match. I mean, they are at the same time location, but they are way off. So, but you will see that as we add more and more Fourier terms, this will become better and better. So let's do that. So we just take this and add this. But remember, this one is 2 times 3. Might be easier to just write a code for this. Right. So we now added the second Fourier coefficient. See what's happening? The peak here is now more enhanced, and we are slowly trying to reach this flat plate here, flat of the k pi, and we are trying to reach that. And we are still seeing some oscillations, but as we add more terms, it will only get better and better. So let's, instead of doing this manually, let me do that constructed. Right. For I is equal to 1 is to n a1 times I into cosine of I minus 1 into 2 into pi over t. Okay. Okay, what did I mess up? It's supposed to be an array. Sorry. Let's get T here. Alright. So let's make this first subtle one term. This is what we saw. And then as we increase this number, we should see it approach better and better and better. So it's better. And then we make it 4. You can see it's reaching better, right? It's trying to get to the peak much more better than as the previous versions. Include 5 terms. And now it's getting closer there. 6. Even better, right? Let's make it 10. Even more closer. 12. Even more closer. So in theory, once you go into infinite number of terms, you should actually be able to exactly capture this signal. Does this make sense, guys? Do you kind of understand what Fourier series is actually trying to do? So as you add more harmonics, it's trying to actually get to the signal and represent it in form of harmonic components. Chandran, can we reset the camera again? I think I lost the video again. Yes, each time we change the number here and add more number here, that means we are adding higher and higher harmonics. So instead of just having up to 12 terms, now we are considering up to 15 terms, which makes it look even closer to the original signal. So as you keep adding more and more and more, it becomes closer and closer to what you see in the actual signal. So in theory, if you had infinite number of terms, then this one would match exactly on top of what the original signal is. Now, what you do see is this extended overshoot and come back down. That does happen when a signal is not continuous, which is the case in this case. You can see that the signal jumps from 0 to 1, and it's difficult for Fourier series to capture that jump because Fourier series essentially contains harmonics and all of them are continuous. You're trying to capture a non-continuous kind of phenomenon using continuous functions, and that doesn't work out very well. However, if your signal is periodic and continuous, then you'll see that Fourier series converges much faster, actually. One lady had a question that why exactly we are doing Fourier series. Do you now understand that the concept behind it, that we are actually trying to introduce harmonics, which can allow us to capture the signal better? Does that make sense? Okay, all right, good. Then this one is, my objective is achieved. That's good. Any more questions about Fourier series so far? Yes, no, no? Okay, cool. All right. So let's come back to this one, and since we have another 5 minutes, let me try to cover something small to finish this chapter today. Okay, so what I did want to say here was there is another way to get the Fourier coefficients in MATLAB. So the way we did is through this integration at every time step, right? For every n, we performed one integration in order to get our Fourier coefficient. But there is a more elegant way to do it, which has been developed in the last decade. It is called fast Fourier transform. And it's going to be a little hard to explain the concept behind fast Fourier transform algorithm. But hopefully, if we have time to touch upon random vibrations, we will be going through the FFT algorithm in a little more detail. So the way FFT works is that you could get the same answer. You can see my screen right now, right? Yes, okay. So we calculated C1, which is the complex Fourier coefficient, using our original approach which we derived in the class. The alternate approach is to use the FFT. So what we do here is take the signal which we had and then take a FFT of the signal, or the fast Fourier transform, and divide it by the number of elements in the signal, original signal, and that already gives you the Fourier coefficients. But the way you do it is basically you take that into account and again go through the same process. So you see these two are exactly the same, C1 and C2, except that instead of C1 we are using C2. So C2 directly gives you the Fourier coefficients for a signal. And FFT is much faster than trying to obtain your coefficients in this way, because this loop requires you to run nx number of times. FFT is a faster algorithm, so you can read about it in MATLAB help. So you can go to the MATLAB command window and type help FFT, and it will give you a section. You can also go online. If you click at reference page for FFT, you can even go to the MATLAB website. And okay, why doesn't it open? You can maybe just go to MATLAB FFT, fast Fourier transform MATLAB, and you can read a little bit more about it here. Okay, and there are some couple of examples which they provide, and I would advise you to definitely go through this page, try to play with it a little bit and see what exactly FFT does. And I am going to upload, hopefully, this particular piece of code onto eCampus, and you can also play with it and see as you increase the number of Fourier coefficients, what happens. So if you want to calculate more than 15, just put maybe 100 here and run it. It takes probably a little longer to run, but nevertheless will run. And maybe in the reconstructed also you are now having 100 signals. Okay. So this is 15. So this, let's make it max. And then it takes 100 of those Fourier coefficients. See what's happening? These lobes which you were seeing, they are now converging into flatter lines. So the more and more you do, the better and better the convergence should be. Right? Okay, so I'll upload this code to eCampus and you can have a run with it and see for yourself. So that's about the fast Fourier transform. And the final thing, I think we have run out of time, so probably we'll discuss that in the next class. We'll be talking a little bit about what we call the vibration terminologies, and a little bit about those vibration terminologies, and then we'll move into our main lecture, which is the free vibration, next week. All right, thank you very much, guys. I'll see you next week.